Hey guys, welcome to Online Learning with Miss Gutierrez. Today I'm going to start with lesson 94 for you guys. We're going to keep moving right along with our lessons as scheduled. So that schedule that you have from me that lines out like when everything is taught and when it's due, that all stays the same, okay? The delivery is just a little bit different because you're going to be watching me here instead of in person. So I miss you guys. I can't wait till we can be back together again, but I am so thankful that we have an opportunity like this to still be able to meet in some ways and like with the Zoom meetings and everything. So this is how we will proceed for now for the time being. And thank you guys for your flexibility and for just being able to adapt to all of this. I know it's actually so much easier for you guys than it is for us old people. So y'all are doing a great job. Hang in there. Save your questions that you have from these lessons to ask me next week whenever we meet together for our Zoom meeting. If it's something urgent, you can always tell ask your parents to email me, or you guys should have my email address too. You're welcome to email me. But let's get started. So this is a long lesson. Excuse me. This is a long lesson. So just a heads up, lesson 94 is probably the longest one that we're going to have to go over this week. So just bear with me, okay? If you start to feel a little bit overwhelmed, you can pause it and come back to it. That's the beauty of doing it this way. So we'll get started and we'll just kind of go right through. There's lots of examples and lots of things to talk about. So probability, we've talked about probability before. This is not a new concept, but probability is just talking about the likelihood of what is going to occur. So you're actually probably hearing a lot of probability in the news right now if you've been watching it at all, which I'm sure your parents have had it on, or if you've just heard your parents talking about what's going on with the coronavirus. There's lots of statistics being tossed around, like talking about the percentages of, how many deaths there are for how many people are getting it, which by the way is really, really low. So don't freak out about that. But there's just a lot of statistics going around because people are trying to figure this whole thing out. And so that's what we base things off of. That's what they're basing the recommendations. The reason that we're not meeting right now is based off of statistics. It's based off of the fact that this virus is at least twice as contagious as the flu. And so knowing that it's way more contagious, so that's a statistic right there. It's, 200% as contagious as the flu. Knowing that statistic right there, and along with the fact that it is causing more severe reactions in some people is what is making people, say we need to have social distancing, we need to be prudent and make these choices in order to stay safe. So that's statistic based, and that's what we're looking at. We're looking at probability. We're going to look at it in a little bit different respect today, but I just kind of wanted to give you a background on how you might be seeing this in your everyday life right now and how you might be hearing it. So what we are going to be talking about though is a little bit more basic. We're going to talk about things like flipping a coin and spinning a spinner and pulling a card out of a deck, okay? So those are going to be the things that you hear me referring to in the examples. So to get started, we are going to talk about flipping a coin. So when you flip a coin, you have two options. You can either flip on the head or you can flip on the tail. Let me see if I can get the glare just right so you can see it. Okay, so we know that we can either have heads or tails. That's two options, right? So from those two options, if you were to flip a coin again, so let's say you got a head on your first flip. If you flip it again, you still have the same options. You could either get a head or a tail on your second flip. Same thing if you got tails the first time and then you flip it again. You could either get heads or tails on your second flip. So then by flipping a coin 2 times, there are actually 4 possible results. So you could get heads, then heads. You could get heads, then tails. You could get tails, then heads. Or you could get tails, then tails. So we call this our sample space. That's a little vocabulary term for you right there. Okay, our sample space is the list of outcomes. So a list of possible outcomes is your sample space. So in this case, these are our sample space. So now if we're trying to find the probability of getting one of these combinations from our sample space, so let's say we want to find the probability of flipping heads, then heads. Well, we would say there's only one combination of heads and heads out of these 4 possible combinations. So that means my probability is 1 out of 4. Another way to look at it would be to say, I know that these 2 actions, these 2 flips are independent of each other. That means one doesn't depend on the other. So what I get from flipping this coin does not in any way determine what is going to happen when I flip the second coin. Okay, it's totally independent. So because of that, I can say, well, I know that the probability of flipping a head anytime I flip a coin is 1/2 because there's 2 options. So 1 out of 2 is the probability of flipping a head. So on the second flip, same thing. The probability is also 1 out of 2. When you're trying to find the probability that both of these things would happen in that order, you have to multiply those individual probabilities, okay? So 1/2 times 1/2 gives us 1/4, which, if you'll notice, should look familiar. It's exactly what we got from looking at our sample space, okay? So just 2 different methods for figuring out the exact same thing. We're gonna use this method where we multiply a lot more though, because in some of the bigger things, you're not gonna wanna be writing all this out, okay? So let me erase a little bit of that. This whole chart that I have right here is actually on page 642 in your book. We're gonna get to that in just a minute, but that's why that's up here. So I'm gonna leave that when I erase some of this other stuff, and you're just gonna kind of have to watch me work around it for now. I didn't want to have to be drawing it while I was trying to teach you. All right, so let's say we were trying to find the probability of flipping heads, then tails. So we could make our big, tree diagram, kind of like what I had going in the beginning, and figure it out from there. Or we could use the multiplication method I just showed you, and that's gonna be a lot simpler. So let's try and implement that. So the probability of flipping a head is 1/2. The probability of flipping a head on the second one is 1/2. The probability of flipping a tail on the third flip is 1/2. So to find the total probability that all these things would happen in that order, I multiply 1/2 times 1/2 times 1/2. 2, be careful here. A lot of you will probably say 2 times 2 times 2 is 6. But remember, you got to multiply one at a time. 2 times 2 is 4. Then 4 times 2 is 8. So it'd actually give us 1/8. Good job. Okay, so let's look at a spinner. Let me show you what a spinner is going to look like. So when we talk about a spinner, think like, when you play Twister or whatever. Okay, so we've got a spinner, 1, 2, 3, 4. Okay, so there are 4 sections. So that means that the probability of spinning, or the little spinner thing landing on any one of these sections, would be 1 out of 4. Okay, so keep that in mind. So if we are asked what is the probability of getting a 2 on this first spin and a 1 on the second spin. So the question is asking us, let me do it up here. What is the probability of getting a 2 and then a 1? Okay, so we could say, all right, well, I know that the probability of spinning a 2 the first time is 1 out of 4. So that's 1/4. The probability of spinning a 1 on my second spin is also 1 out of 4 because there's only one space out of the 4. Y'all see that? So that would be 1/4. So then we multiply, because the rule is just to always multiply when you're finding compound probability, okay? 1/4 times 1/4 equals 1/16. All right, so that means that there are 16 possibilities, possible combinations when I do 2 spins, and only one of them would result in giving us a 2 and then a 1, okay? So it's like, not super likely to happen. So let's look at a different scenario. And again, this was another example of independent outcomes or independent events, okay? 2 things that are not related to each other, do not rely on each other. The first spin does not rely, or the second spin does not rely on the first spin, okay? The first spin in no way determines what the second spin is going to result in. So if we were asked, if we talk about dot cubes, so they call them dot cubes. If you look at my little chart here, they look like dice. That's what they are. They're dice. I don't know why they call them dot cubes or number cubes. I don't know. We just go with it. We just say what they, say, okay. All right, so we are given these little dot cubes. So this row up here is like your first roll. So when you roll the first cube, okay? This one over here is going to be your second cube. So imagine that you're rolling 2 dice, okay? You're rolling a first one and a second one, okay? And then these are the results, possible results. So the first one could end up being a 1, 2, 3, 4, 5, 6. The second one could end up being a 1, 2, 3, 4, 5, 6, okay? Notice that there's only one of each number on each cube, okay? So these combinations in here tell us the total of those 2 given results. So like if you landed a 1 with your first cube and a 1 with your second cube, the total of 1 plus 1 is 2. If you landed a 3 with your first cube and a 1 with your second cube, the total of those results is 4. Y'all see how this works? So that little chart is on page 642 in your book. So you're going to want to use that for at least for some of these, but possibly on your homework too. So just keep that in mind. You don't want to be drawing this out every single time, trust me. I've drawn it out like 4 times now because my baby keeps coming and erasing it. It's kind of annoying. Okay, but he's adorable, so he gets away with it. Anyway, so let's look at if a pair of dot cubes is tossed once, what is the probability that the total number rolled will be 12? So we want to find the probability that the total is 12. So think with me here. If we need for the total to be 12, there is only one way. We don't even have to look at the chart really to think about this. There's only one way that you can put 2 number cubes together to give you 12, and that's a 6 and a 6, okay? So 6 and a 6 are the only combination of number cubes that are gonna give you a 12. So we would have to get a 6 and a 6, okay? Now, the probability of getting a 6 on the first roll, there's only one 6 out of 6 possible results. So the probability of getting a 6 would be 1/6. The probability of getting a 6 on the second roll, there's only one 6 out of 6 possible results. So that would also be 1/6. So then again, our rule is to multiply. So we're going to multiply our probabilities, our independent probabilities. So 1/6 times 1/6 gives you 1/36. Okay, so we can also look at our chart to see that here. 6 and 6 gives us 12. There's only one 12 on this chart out of 36 numbers. There's a little bit of a glare on it. Sorry, guys. Let me see if I can move it around. Oh, there we go. There we go. Good. All right, so there's only 112. If you count up all these squares, there's 36 of them. So there's only 112 out of 36. So that's 1 out of 36, which we already figured out doing it this way. Okay, so the charts just kind of get to give you extra visualization. All right, so now we are asked, what is the probability of rolling a total greater than 9? So we want our total to be greater than 9. Let's see if I can do that without erasing it all. So this is where it's helpful to use the chart. So it's not greater than or equal to 9, it's just greater than 9. So we want to look at all the values that are greater than 9. So we can count them up. We've got 1, 2, 3, 4, 5, 6 values that are greater than 9. So that's going to be 6 possibilities out of, we already said there's a total of 36 values here on the chart. So now, you don't have to do anything else, but you do have to reduce. So we're going to reduce 6 over 36. We know that both of those values will divide evenly by 6. 6 divided by 6 is 1. 36 divided by 6 is 6. So actually, the probability that you would get a sum or a total greater than 9 would be 1/6. All right, so we're going to move away from the dot cubes and away from independent events. And we're going to talk for a second about dependent events. We're almost done. Hang in there, guys. I know I told you this was a long lesson. We've got like 2 more examples that we need to go over, okay? So you're doing great. So I'm going to go ahead and erase all of this because we actually don't need our dot cube anymore, and that'll free up some more space for me to work. So now we're going to talk about cards, okay? It always surprises me how many students have no idea what a deck of cards is made up of. So you guys might know, or you might not. So let's just talk about this real quick. If you've got a deck of cards, you've got 4 suits. So you've got spades, clubs, hearts, and diamonds. So those are your 4 suits. Each of those 4 suits has all the same cards. So it starts at a 2 and goes all the way to an ace. So 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. Okay, for each suit. So there's a total of 52 cards. Even if you've never played with cards, chances are you've heard the phrase 52 card pickup as a game. That's where it comes from. There are 52 cards in a deck. So there are 52 cards in a deck. Okay, and there are 4 suits. Okay, meaning there are 4 of each card. So there are 4 of each card. And there are 13 cards in each suit. Okay, so that's just kind of a breakdown, just to kind of give you a background before we talk about the probabilities. So the question stated in example 5 is, from a well-mixed deck of cards, Josephina selected and kept 1 card, then a 2nd card, then a 3rd card, and finally a 4th card. What is the probability that the 4 cards Josephina selected are aces? Okay, so we are looking at 4 different events here. So she's picking 4 different cards, and we want to know the probability that she gets an ace, then an ace, then an ace, then an ace, okay? So to do that, we have to think about, well, how many aces are in a deck? Well, we just talked about how there are 4 of each card. So we're starting with 4 aces out of 52 possibilities, okay? Then, remember we're multiplying here. Then for our second pick, the important phrase here is that she kept the cards. So as she's drawing them, she kept them. Where can I write this? Kept them. Kept is important because that signals that it's a dependent situation, okay? So because she kept that first ace once she drew it, she's not putting it back in the 52 cards. So now she's only picking from 51 cards, and she wants an ace again. So she already pulled 1 ace out. So now there's only 3 aces left. So now her probability of getting an ace is 3 out of 51. Same thing happens again. She's keeping this card out. So now there's only 50 cards to choose from, and only 2 of them are aces. So there's only 2 aces left in the deck because she already took out an ace here and an ace here. Now for the final one, she's already taken out 3 aces. So now there's only 49 cards left total, and there is only 1 of them that is an ace. So this is different from what we saw with independent events, because independent events didn't affect each other. So it would have just like stayed 52, 52, 52, 52. If she was replacing the card instead of keeping the card out, it would be independent. So it would just stay 52, 52, 52, 52. But she's not putting it back. She's keeping it. So that affects our other draws, okay? So then all we have to do is multiply this, which is going to look really ugly. I'm just going to go ahead and give you the answer because I know you know how to multiply, but it would end up being 1 over 270,725. So if you've ever watched like World Series of Poker or anything like that, I actually love this stuff. It's so interesting. They give you stats the whole time. So this means that in order to pick 4 aces in a row out of a deck, that will only happen 1 out of 270,725 tries. That's pretty unlikely. All right, so that's why it's a big deal, like when you have a hand like that, because it's very, very rare. Okay, last one. We're almost done. I told you we were getting super close. All right, so I actually really like this one. And we're just going to talk about it real quick. It kind of gives you, if you want to read example 6 and the little section in front of it on page 644, it talks about using the calculator. Okay, we don't use a calculator a ton in this class, but for this, it would be a good example of when to use it. The question says, find the probability of correctly guessing the answer to every question on a 20-question 4-option multiple choice test. So if you've ever heard that phrase like, oh, abacadabra, it works every time. You can just like guess those in that order and it'll get you at least, this percent right. Well, we're about to debunk that myth. So if you were to guess on every single question of a 20-question test, and there are 4 possible answers on each one, well, we could write this out. It would be, so in the first question, you've got 1/4 a possibility of getting it right. On the second question, 1/4 possibility of getting it right. Third question, 1/4 possibility of getting it right. We could go on and on and on and on because there's 20. So we would have to write it out 20 times. But if you notice, these are independent events, so we're multiplying the same thing over and over again. When we multiply the same thing by itself, we've seen this before, that's using a power. We can rewrite this using a power, right? So instead of writing it on and on and on 20 times, we can write 1/4 to the 20th power. If you type that in your calculator, you will end up with 1 over 1.1 times 10 to the 12th power. That means that is less, the probability of you getting every question right by guessing is less than 1 in a trillion. That's pretty bad odds. So do your homework and don't guess on your tests. And that's a good place to end for today. So good job. Happy homework. I'll see you on lesson 95.